Imagine standing at the edge of space, looking down at the earth below you. Before we go any further, if you want a brand new earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From up there, the planet looks smooth and soft, like a blue marble wrapped in thin white cloud. But look closer. Along the edges of continents, cutting across the middle of great land masses, you can see them. Long, dark, wrinkled lines running across the surface of the world. Those are the mountains. They rise from every continent. They run beneath every ocean. They exist on frozen poles and in the middle of hot deserts. Right now, as you listen to this, mountains are being built. Slowly, quietly, with enormous force, the ground beneath your feet is moving. It has been moving for billions of years, and it will keep moving long after we are gone. The earth is not a solid, still ball of rock. It is layered like an egg. The outer shell, called the crust, is the thin layer of rock we walk on. Beneath it sits the mantle, a thick zone of hot rock that moves very slowly, almost like thick honey left in the sun. And at the very center of the earth burns the core, a ball of iron so hot that the numbers are hard to imagine. The inner core reaches temperatures close to 9,000 degrees Fahrenheit. That is nearly as hot as the surface of the sun. All of that heat has to go somewhere. It pushes upward through the mantle in slow, churning currents. Those currents drag the crust along with them, and the crust does not move as one piece. It is broken into massive sections called tectonic plates, giant slabs of rock that fit together like pieces of a cracked eggshell. There are about 15 major plates, and they are always moving. Most of them drift only an inch or two each year, about as fast as your fingernails grow. But an inch a year, over millions of years, adds up to something extraordinary. When two plates push toward each other, the rock between them has nowhere to go but up. It folds, it buckles, it crumples like the hood of a car in a slow-motion collision. Over millions of years, that crumpling builds ridges. Those ridges grow taller, and eventually they become mountains. The Himalayas, the tallest mountain range on Earth, were born this way. The Indian plate has been pushing into the Eurasian plate for about 50 million years. That collision is still happening right now. The Himalayas are still growing, rising a few millimeters each year. Not all mountains are born from collisions, though. Some rise when the crust is pulled apart rather than pushed together. When plates move away from each other, the rock in between can crack and drop, leaving tall walls of stone standing on either side. These are called fault block mountains, and the Sierra Nevada Range in California is one of the most beautiful examples on Earth. Those pale granite peaks, glowing gold in the late afternoon light, rose from the ground as the crust stretched and fractured beneath them. And then there are the mountains born from fire. When magma, the molten rock deep inside the earth, forces its way up through a crack or a weak spot in the crust, it piles up at the surface. Each eruption adds more material. Over time, that pile grows into a cone, a peak, a mountain made entirely of cooled lava and ash. Mount Fuji in Japan is this kind of mountain. So is Mount Kilimanjaro in Africa, rising alone from the flat plains of Tanzania, its snow-capped summit visible from nearly 200 miles away. 3 different processes, 3 different kinds of mountains, and yet they all come from the same source, the restless, churning energy of a living planet. That is what makes mountains so remarkable. They are not accidents. They are the visible record of forces so large and so old that the human mind can barely hold them. Every ridge, every cliff face, every sharp peak pointing into the sky is the result of millions of years of pressure, heat, and slow, patient movement. The mountains are the earth telling its own story, written in stone. And tonight, as you settle in and let your breathing slow, those mountains are still out there, still rising, still wearing down under wind and rain and ice, still being born and still returning, grain by grain, back to the sea. Beneath your feet right now, the ground is moving. Not fast enough to feel, not fast enough to see, but moving all the same, the way a clock hand moves steadily, without stopping, in a direction you can only notice if you look away and look back again. The Earth's outer shell is not one solid piece. It is broken into large sections called tectonic plates, thick slabs of rock that float on top of a deeper layer of hot, slow-moving stone. Think of it like ice on a pond. The ice looks solid. It looks still. But underneath, the water is always shifting, always pushing, and eventually the ice moves too. There are about 15 major tectonic plates on Earth, along with several smaller ones. Some of them carry continents on their backs. Others lie beneath the ocean floor. The largest is the Pacific Plate, which covers more of the Earth's surface than any single continent. It stretches across most of the Pacific Ocean, and it is moving right now, sliding slowly toward the northwest at roughly the speed your fingernails grow. That comparison is not a joke. Scientists measure the movement of tectonic plates in centimeters per year. Most plates move between 2 and 10 centimeters annually. Your fingernails grow about 3 to 4 centimeters per year. So when you imagine a mountain range rising over 50 million years, you are imagining something that grew at roughly the pace of a human fingernail, never stopping, never resting, across a stretch of time so long it contains the entire history of our species many times over. The plates float on a layer called the mantle, that thick zone of hot rock sitting between the Earth's crust and its deep iron core. The mantle is not liquid exactly. It is solid rock, but under enormous heat and pressure, it behaves a little like very thick syrup. Over millions of years, it flows, slowly, deeply, in great looping currents driven by heat rising from the core below. These currents are what push the plates. The heat from the center of the Earth drives everything that happens at the surface. The core itself sits roughly 6,000 kilometers below where you are lying right now. The outer core is liquid iron and nickel, swirling in slow motion. The inner core is solid iron, squeezed so hard by the weight of everything above it that it cannot melt, even at temperatures near 5,000 degrees Celsius, nearly as hot as the surface of the sun. That heat bleeds outward through the mantle, driving the slow circulation that pushes the plates, that builds the mountains, that shapes the world you see when you look out a window. The crust, the thin, cool, rocky skin of the Earth, where all life exists, varies in thickness. Under the continents, It runs about 30 to 50 kilometers deep. Under the ocean floors, it is much thinner, sometimes only 5 to 10 kilometers. If the Earth were the size of an apple, the crust would be thinner than the apple's skin. Everything we have ever built, every mountain we have ever climbed, every ocean we have ever crossed, sits on that thin outer layer. And that layer is always in motion. The plates do not move in the same direction. Some pull apart from each other. Some slide past each other sideways, grinding and shaking. And some push directly into each other head-on, with a force so immense that the rock has nowhere to go but up. That last kind of collision is where most of the world's great mountain ranges were born. The idea that continents move was once considered absurd. A German scientist named Alfred Wegener proposed it in 1912. He noticed that the coastlines of South America and Africa fit together like puzzle pieces. He noticed that the same ancient fossils appeared on continents separated by thousands of miles of open ocean. He spent years arguing that the continents had once been joined and had slowly drifted apart. Most scientists of his time rejected the idea completely. It was not until the 1960s, when ocean floor mapping revealed the spreading ridges beneath the sea, that the scientific world accepted what Wegener had seen. The plates are real. The motion is real. And the mountains rising from that motion are the most visible proof we have that the earth beneath us is alive. Every range, every ridge, every peak you have ever seen or imagined is rooted in this truth. The ground is not still. It never has been. And the mountains are the places where that restlessness rises high enough to touch the sky. Of all the mountains that rise from this restless earth, the fold mountains are the most common. They are also, in many ways, the most astonishing. Their story begins not with fire or explosion, but with something far quieter. It begins with pressure. Slow, immense, patient pressure, building across millions of years. Picture two great tectonic plates, those massive slabs of rock that make up the outer shell of the earth, moving toward each other. They move only a few centimeters each year. That is roughly the speed at which your fingernails grow. It sounds like nothing. But But when you multiply that motion across tens of millions of years, the force that builds is almost impossible to imagine. When the plates meet, the rock between them has nowhere to go. It cannot sink easily. It cannot spread sideways. So it does the only thing it can. It bends. It buckles. It folds upward, like a rug being pushed from both ends across a smooth floor. The layers of rock, which once lay flat and horizontal at the bottom of ancient seas, begin to ripple and rise. Over time, those ripples grow into ridges. Those ridges grow into mountains. This is how fold mountains are born. The Himalayas are the most famous example on Earth. They formed when the plate carrying the Indian subcontinent collided with the plate carrying Asia. That collision began roughly 50 million years ago. The Indian plate was moving north at a steady pace, and it has not stopped. Even today, the Himalayas are still rising. Scientists estimate they grow by about 5 millimeters each year. The mountains are not finished. They are still being made. What makes this even more remarkable is what the rock of the Himalayas contains. High on the slopes of these peaks, at elevations where the air is thin and the cold is fierce, explorers and geologists have found marine fossils, the remains of ancient sea creatures locked inside the stone. Shells, coral, the bones of animals that once lived at the bottom of a warm, shallow sea called the Tethys Ocean. That ocean no longer exists. It was consumed by the very collision that built the mountains. The seafloor was pushed upward, carrying its ancient life with it, until it sat miles above the ocean that had once been its home. The top of the world was once the bottom of the sea. The Alps of Europe tell a similar story. They formed when the African plate pushed northward into the Eurasian plate, beginning around 35 million years ago. The rock crumpled and folded into the sharp, gleaming peaks that today stretch across Switzerland, Austria, France, and Italy, the Andes of South America, the longest mountain range on land, formed through a related process as the oceanic Nazca plate drove beneath the South American plate, forcing the continent's western edge upward into a spine of peaks that runs nearly the full length of the continent. The Rockies, the Atlas Mountains of Africa, the Zagro's mountains of Iran. All of them fold mountains. All of them born from the same slow, grinding patience of colliding stone. The rock inside a fold mountain carries the memory of everything it has been through. Geologists can read those memories like pages in a book. The layers of stone, called strata, show where the rock was once flat. The angle at which those layers now tilt tells how far the fold has progressed. Some layers have been bent nearly vertical. Some have folded completely over on themselves, so that older rock ends up sitting on top of younger rock. The earth keeps its own records, written in stone, and the mountains are among the oldest and most detailed entries. There is something deeply calming about this process when you sit with it long enough. The violence of it is real. The forces involved are staggering. But it all happens so slowly. No single moment of drama. No sudden event that you could witness and survive. Just the quiet, relentless work of time and pressure. Year after year, century after century, until something that was once flat and submerged beneath a warm sea stands sharp and white against a cold blue sky. The fold mountains remind us that the earth is not a fixed and finished thing. It is a process. It is always in the middle of becoming something new. The stone beneath your feet right now is part of that process. It is moving, bending, shifting, just too slowly for any one life to notice. But the mountains notice. They are the record of every push, every fold, every slow and patient rise. They are the earth remembering out loud. Not every mountain rises from a fold. Some are born from a break. Deep in the earth's crust, the rock is not always smooth or continuous. It is crossed by long, deep cracks called faults. A fault is simply a fracture in the rock where two sections have moved against each other. These fractures can run for hundreds of miles. Some of them are visible at the surface as long, clean lines across the land. Others are buried far below, invisible from above, but still active, still moving, still shaping the ground we walk on. When the crust is pulled apart rather than pushed together, something different happens. Instead of folding and buckling upward, the rock breaks. It splits along those fault lines. One block of crust drops down, Another stays in place or rises. The block that stays high becomes a fault block mountain. The block that drops becomes a valley. This process is called rifting, and the mountains it creates have a very different look from fold mountains. They tend to have one steep, sharp face where the fault line runs, and one long, gentle slope on the other side. The Sierra Nevada in California is one of the finest examples on Earth. The Sierra Nevada is a single enormous block of granite that tilted upward along a fault on its eastern edge. Granite is a hard, pale rock made mostly of minerals called quartz and feldspar. It forms deep underground when molten rock cools very slowly, and the slow cooling gives the crystals inside time to grow large. When you look at a piece of granite up close, you can see those crystals glittering, pale pink and silver and gray, packed tightly together. The Sierra Nevada is essentially a tilted slab of this ancient crystallized rock, now standing thousands of feet above the desert floor. Its eastern face drops sharply, almost like a wall. Its western slope rolls down gently toward the sea. The minerals inside that granite carry a story that reaches far beyond Earth. Quartz is made of silicon and oxygen, two of the most common elements in the universe. Feldspar contains aluminum, potassium, and sodium. These elements were not made on Earth. They were forged inside stars that lived and died long before our sun was born. When those stars collapsed and exploded, they scattered their material across space. Over millions of years, that scattered material gathered together under gravity, forming our solar system, our planet, and eventually the rock beneath the Sierra Nevada. The granite in those mountains is, in a very real sense, stardust that has been compressed and crystallized by time. The Great Basin, the broad, dry region that stretches across Nevada and into neighboring states, was shaped almost entirely by fault block activity. Here, the crust has been stretched and pulled apart over millions of years. The result is a series of parallel mountain ranges separated by flat valleys, like a rumpled blanket laid across the desert floor. Scientists count more than 400 individual mountain ranges within the Great Basin. Each one is a separate block of crust that rose while the valleys between them sank. The whole region sits at high elevation, yet it feels low and open because the mountains rise from an already elevated base. The East African Rift Valley tells a similar story on a much grander scale. Here, the African continent is slowly being pulled apart along a massive fault system that runs for thousands of miles. The rift has created some of Africa's tallest mountains, including the Ruwenzori Range, whose peaks are often hidden in cloud and draped in glaciers. The same rift has also created some of the deepest lakes on Earth, like Lake Tanganyika, which plunges more than 4,700 feet to its floor. The mountains and the lakes are part of the same event, the same slow tearing of the crust, just expressed in opposite directions. One goes up, one goes down. Both are made by the same fracture in the same rock. There is iron in that rock too. Iron is one of the most abundant elements in the Earth's crust, and it was also forged in dying stars. The iron in the mountains, the iron in the soil, the iron in your own blood, all of it shares the same origin. It was made in the heart of a star that no longer exists. When that star died, it gave its iron to the universe, and the universe gave it to us. Fault block mountains remind us that the Earth does not always build by pushing. Sometimes it builds by breaking. And in the breaking, something new and lasting rises from the gap. The fractures are not failures. They are openings. They are the places where the Earth finds a new shape. Not all mountains are born from pressure or from breaking. Some mountains are born from fire. Deep beneath the Earth's surface, there is rock so hot that it melts. This melted rock is called magma. It sits in great pools and chambers far below the ground, under enormous pressure from the weight of everything above it. When that pressure finds a crack, a weakness, an opening in the crust, the magma moves upward. It rises slowly at first, then faster, pushing through solid rock the way water pushes through a cracked dam. When it finally breaks through the surface, we call it lava. And when that lava cools and hardens, layer by layer, over thousands and millions of years, it builds something enormous. It builds a volcanic mountain. This is one of the oldest ways the Earth has ever made new land. volcanic mountains are not carved or folded or fractured into shape. They are added to piece by piece, eruption by eruption, until the pile of cooled lava becomes a peak that touches the clouds. The shape of a volcanic mountain depends on what kind of magma feeds it. Magma that is thin and runny, low in a mineral called silica, tends to flow easily across the ground before it cools. Mountains built from this kind of lava have wide, gently sloping sides, like an upside-down shield lying flat on the ground. Scientists call these shield volcanoes. Mauna Loa in Hawaii is one of the finest examples on Earth. It rises from the ocean floor with long, smooth slopes that spread for hundreds of miles. It does not look dramatic from a distance, but it is, by volume, the largest volcano on the planet. Other magma is thick and sticky, rich in silica, and it does not flow easily. It builds pressure inside the volcano instead of escaping smoothly. When it finally erupts, it explodes outward with tremendous force, throwing ash and rock high into the sky. The lava that does flow cools quickly and piles up steeply near the vent. Over many eruptions, these volcanoes grow tall and narrow, with steep sides and a sharp peak. Scientists call them stratovolcanoes or composite volcanoes. Mount Fuji in Japan is one. Mount St. Helens in Washington State is another. These are the mountains that most people picture when they think of a volcano. Tall, cone-shaped, beautiful, and dangerous. The heat that drives all of this comes from two places. Some of it is leftover warmth from when the Earth first formed, more than 4 billion years ago, when the planet was a ball of colliding rock and metal, glowing orange with the energy of its own creation. Some of it comes from radioactive decay, the slow breakdown of elements like uranium and thorium deep inside the Earth, which releases heat as they change into other elements over billions of years. The Earth is still warm from its own birth. It has been cooling for 4 billion years, and it is still not done. That heat is not evenly spread. In some places, columns of especially hot rock rise up through the mantle. The thick layer of hot rock between the crust and the core, like slow bubbles in a pot of thick soup. Scientists call these columns hotspots. When a tectonic plate moves over a hot spot, the heat punches through the crust and builds a volcano. Then the plate keeps moving, and the hot spot punches through again in a new spot, building another volcano. Over millions of years, this process creates a chain of volcanic islands, each one older than the last. The Hawaiian Islands were made exactly this way. The big island of Hawaii sits over the hot spot right now, which is why it still has active volcanoes. The older islands to the northwest have drifted away from the heat source. Their volcanoes have gone quiet. They are slowly being worn down by rain and wind and time. Volcanic mountains also rise along the boundaries where tectonic plates collide. When one plate dives beneath another, a process called subduction, the descending plate carries water and minerals down into the hot mantle. That water lowers the melting point of the rock around it, and magma forms. It rises, and it builds volcanoes along the edge of the overriding plate. The ring of fire, the long curved chain of volcanoes that circles the Pacific Ocean, was built this way. It stretches from New Zealand up through Japan, across to Alaska, and down the western coasts of North and South America. More than 75% of the world's active volcanoes sit along its arc. Fire builds mountains, and the same fire that once threatened to consume the surface of the young Earth now quietly shapes the peaks we call beautiful. Now think about what all that fire and force has actually built. Think about the peaks that rose from all that slow, grinding, volcanic work. The tallest mountains on Earth are staggering things. They are so tall that the human mind struggles to hold the number. Mount Everest stands 29,032 feet above sea level. That is the official height measured by a 2020 survey using GPS technology. To put that in terms you can feel, if you stacked the Empire State Building on top of itself more than 19 times, you would just barely reach Everest's summit. The air up there is so thin that each breath delivers only about a third of the oxygen you would get at sea level. Without bottled oxygen, most people lose consciousness within minutes. Everest sits in the Himalayas, the great mountain range that runs along the border of Nepal and Tibet. The Himalayas Himalayas were born from a collision. Around 50 million years ago, the Indian tectonic plate crashed slowly into the Eurasian plate. That collision is still happening today. The Indian plate pushes north at roughly 1.7 inches per year, and Everest rises a tiny fraction of an inch each year because of it. The mountain is not finished. It is still growing, grain by grain, season by season. But Everest is only the tallest mountain measured from sea level. If you measure from the center of the earth, a different peak wins. Chimborazo, a volcano in Ecuador, sits very close to the equator. Because the Earth bulges slightly at its middle, the equator is farther from the planet's core than the poles are. Chimborazo's summit is about 3,967 miles from Earth's center. Everest's summit is only about 3,965 miles from the center. By that measure, Chimborazo's peak is the farthest point from the heart of the Earth. It reaches closer to space than any other place on the surface of our planet. The Himalayas hold more than just Everest. They hold 14 peaks that rise above 26,247 feet. Climbers call these the 8,000ers, named for their height in meters. K2, which sits on the border of Pakistan and China, is the second tallest at 28,251 feet. K2 is considered far more dangerous than Everest. Its steep, icy faces and violent weather have claimed the lives of many climbers. For every 4 people who have reached its summit, roughly 1 has died trying. The Andes of South America form the longest mountain range on land. They stretch about 4,500 miles from Venezuela in the north, all the way down to the southern tip of Argentina. That is roughly the distance from New York City to London and back again. The Andes were also built by subduction, the same process that built the Ring of Fire. The Nazca tectonic plate dove beneath the South American plate, and the pressure pushed the land upward into peaks. The highest point in the Andes is Aconcagua in Argentina, which rises to 22,838 feet. It is the tallest mountain in both the western and southern hemispheres. Africa has its own great peak. Kilimanjaro in Tanzania rises 19,341 feet above the surrounding plains. It is a volcano, and it stands almost entirely alone. There is no mountain range around it. It simply rises from the flat savanna like a great dome of stone and ice, its white-capped summit visible for miles in every direction. The glaciers on Kilimanjaro have been shrinking for decades. Scientists estimate that the ice fields there have lost more than 85% of their coverage since 1912. The mountain that once gleamed white may one day stand bare. North America's tallest peak is Denali in Alaska, which rises to 20,310 feet. What makes Denali remarkable is not just its height above sea level, but its sheer vertical rise from its base. Measured from base to summit, Denali rises about 18,000 feet from the surrounding lowlands. That makes it the tallest mountain in the world by that measurement, taller even than Everest, which sits on the already elevated Tibetan Plateau. Everest rises roughly 12,000 feet from its base. Denali simply climbs higher from where it starts. All of these peaks, so different in shape and origin and location, share one quiet truth. They were all pushed upward by the same restless energy moving through the earth. Plates collide, magma rises, rock folds and fractures and lifts. The planet has been doing this for billions of years, and the result is a world edged with stone towers that catch the clouds and hold the snow and feed the rivers below. Every great peak is a record of enormous force, written in rock, standing in the open air for anyone who looks up to read. So how do we actually measure these great stone towers? It seems like a simple question. You find the top, you find the bottom, you measure the distance between them. But mountains have a way of making simple things complicated. The most common way to measure a mountain is by its elevation above sea level. Elevation means how high a point sits compared to the average level of the world's oceans. This is the number most people know. Everest's 29,032 feet. Denali's 20,310 feet. These numbers tell us how far above the sea that summit sits. They are useful numbers, but they do not tell the whole story. Sea level itself is not perfectly flat. the ocean's surface bulges and dips, depending on what lies beneath it. Gravity pulls the water differently in different places. A massive underwater mountain range can actually pull the ocean surface slightly toward it, creating a gentle rise in the water above. This means sea level is really an average, a smoothed out estimate of where the ocean would sit if it were perfectly calm and still across the entire planet. Scientists call this imaginary surface the geoid, which simply means the true shape of Earth's gravity field. Measuring mountains against this surface gives us a more honest picture of their true height. When you measure from the center of the Earth outward, a different mountain takes the crown. Mount Chimborazo, a dormant volcano in Ecuador, sits very close to the equator. Earth is not a perfect sphere. It bulges slightly at the equator because of the planet's spin, the same way a ball of soft clay would widen at its middle if you spun it fast. This equatorial bulge means that points near the equator are already farther from Earth's center than points near the poles. Chimborazo rises to only 20,564 feet above sea level. But because of where it sits on this wider part of the Earth, its summit is about 3,967 miles from the center of the planet. Everest's summit, by the same measurement, is about 3,965 miles from the center. Chimborazo wins by roughly 2 miles, simply because of where it stands on the spinning globe. There is something quietly wonderful about that. The tallest mountain in the world depends entirely on how you ask the question. Measuring a mountain's base is its own challenge. On land, the base is often buried under other rock, or it slopes so gradually into surrounding hills that no clean line exists. Scientists use topographic maps, which are maps that show the shape of the land, using lines that connect points of equal elevation. These contour lines, as they are called, crowd together where slopes are steep and spread apart where the land is gentle. A mountain drawn in contour lines looks like a series of nested rings, each one marking a step in the climb. The closer those rings sit to each other, the sharper the rise. From above, a mountain range drawn in contour lines looks like a crumpled piece of paper slowly unfolding. The ridges and valleys show themselves as long curved lines running parallel to each other, then splitting, then meeting again. It is one of the most honest pictures of the land that exists. No color, no texture, just the pure shape of the earth laid flat on a page. Modern technology has changed how we see mountains entirely. Satellites now carry instruments that bounce radar signals off the surface of the earth and measure the time it takes for those signals to return. From those tiny differences in time, scientists can calculate elevation to within inches. The entire surface of the planet has been mapped this way. We now have a picture of Earth's terrain so detailed that you could trace the path of a single glacier or find the outline of a buried river valley that dried up 10,000 years ago. This kind of mapping revealed something surprising. Many mountains we thought we knew well turned out to be slightly different in height than we believed. Everest itself has been remeasured several times. In 2020, China and Nepal jointly announced a new official height of 29,031.7 feet, about 3 feet taller than the previous measurement. The mountain did not grow. Our tools simply got better. And that is part of what makes measuring mountains so interesting. The mountain stands still. It is patient. It has been standing for millions of years and will stand for millions more. It is we who keep returning with better questions, better instruments, better ways of listening to what the rock is telling us. Every measurement is a conversation between human curiosity and the quiet permanence of stone. The mountain does not change its answer. We just keep learning how to hear it. But the mountains we can see and measure from the surface tell only part of the story. Beneath the ocean, hidden under miles of cold, dark water, there is an entire world of mountains that most people never think about. They are real. They are enormous. And in some ways, they are even more dramatic than anything rising above the ground. The ocean floor is not flat. It is not a smooth, featureless plain stretching endlessly into the dark. It is rugged and wild, cut through by deep valleys, and lifted by enormous ridges and peaks. Scientists have mapped much of it using sonar, a technology that sends sound waves down through the water and listens for the echo when those waves bounce off the seafloor, the time it takes for the sound to return tells researchers how deep the water is at any given point. Over decades, ship after ship has crossed the oceans, sending these pulses downward, slowly building a picture of what lies below. What that picture revealed is astonishing. Running along the bottom of every major ocean is a chain of underwater mountains called the Mid-Ocean Ridge System. This ridge stretches for roughly 40,000 miles, winding around the globe like the seam on a baseball. It is the longest mountain range on Earth. The Himalayas, the Andes, the Rockies, none of them come close in total length. Most of this range sits 2 miles or more beneath the surface, completely invisible from shore, known only through instruments and the patient work of oceanographers. The mid-ocean ridge forms for the same reason mountains form on land. Tectonic plates, the giant slabs of rock that make up Earth's outer shell, are always moving. At the mid-ocean ridge, 2 plates are pulling apart from each other. As they separate, hot melted rock called magma rises up from below to fill the gap. It cools. It hardens. It builds. Over millions of years, this process has piled up enormous amounts of volcanic rock, creating a mountain range that circles the entire planet beneath the sea. Some of these underwater peaks are truly massive. The tallest mountain on Earth, measured from its base to its summit, is not Everest. It is Mauna Kea, a volcano rising from the floor of the Pacific Ocean near the island of Hawaii. From its base on the seafloor to its peak above the water, Mauna Kea stands about 33,500 feet tall. Everest, measured from sea level, reaches 29,032 feet. But Mauna Kea's base sits far below the ocean surface, so most of its height is hidden. Only about 13,800 feet of it rises above the waves. The rest is submerged, vast and silent in the dark water. The ocean also holds something called seamounts. These are underwater volcanoes that rise from the seafloor but never quite reach the surface. There are estimated to be more than 100,000 of them scattered across the ocean floor. Some rise thousands of feet. They create their own small ecosystems, their rocky slopes providing surfaces where coral and sea creatures can attach. and grow. A seamount in the middle of the open ocean acts like an island for deep-sea life, drawing fish and marine animals from the surrounding water. There is also a feature called a geo, pronounced geo, which is a seamount with a flat top. Scientists believe these flat tops were once volcanic islands that rose above the ocean surface long ago. Waves slowly wore down their peaks over thousands of years, shaving them flat. Then, as the ocean floor shifted and sank under its own weight, these flattened peaks slipped below the surface. They carry the evidence of their time above water in their shape. Even now, miles below the waves. The deepest places in the ocean are not flat plains either. They are trenches, long, narrow valleys, where one tectonic plate slides beneath another. The Mariana Trench in the Pacific Ocean reaches a depth of about 36,000 feet. That is deep enough to swallow Everest entirely, and still have more than a mile of water above its summit. The pressure at that depth is crushing, more than 1,000 times the pressure we feel at the surface. All of this, the ridges, the seamounts, the geos, the trenches, is part of the same restless system that builds mountains on land. The same forces that pushed the Himalayas skyward are also shaping the seafloor. The planet does not separate its work into neat categories. It builds and breaks and reshapes in every direction, above the water and below it, in the light and in the dark, always moving, always changing, always making something new from what came before. And this restless energy, this drive to build and break and reshape, is not something that belongs to Earth alone. Other worlds have mountains too. Some of them make our tallest peaks look small. The same forces that crack and fold and push stones skyward here have been at work across the solar system for billions of years. Gravity pulls, heat rises, rock fractures. These are not Earth's rules. They are the universe's rules. Mars holds the tallest known volcano in the solar system. It is called Olympus Mons, and it rises about 72,000 feet above the Martian plains. That is nearly 3 times the height of Everest. Its base is so wide that if you stood at its edge, the far side would be below the horizon. You could not see it all at once. The mountain is simply too large for the human eye to take in from the ground. Scientists believe Olympus Mons grew so tall because Mars does not have moving tectonic plates the way Earth does. On Earth, a tectonic plate slowly carries a volcano away from the hot spot beneath it, spreading the eruptions across many peaks over millions of years. On Mars, the crust stayed still. The same hot spot kept feeding the same volcano over and over for hundreds of millions of years. The lava just kept piling up. Earth's mountains, by contrast, are always being moved and worn and remade. That constant motion keeps any single peak from growing too tall. Our planet's restlessness is also its limit. Venus has mountains too. The Maxwell-Montes Range on Venus rises about 36,000 feet above the planet's average surface level. That puts it in the same rough company as the Himalayas. Venus is a world of crushing heat and thick clouds of sulfuric acid. But beneath all of that, its surface is shaped by the same kinds of forces we see on Earth. Volcanic activity, tectonic stress, the slow movement of heat from the planet's interior, pushing up through the crust. Scientists are still studying whether Venus has active volcanoes today. Evidence suggests it might. The planet's surface is geologically young in many places, which means something has been resurfacing it, smoothing over old features and building new ones. Even our moon has mountains. The lunar highlands are ancient, heavily cratered regions that rise several miles above the moon's lower plains. These mountains did not form the way Earth's did. They were not pushed up by colliding plates. They are the original crust of the moon, left standing after billions of years of impacts blasted away the lower ground around them. They are mountains made by subtraction, not addition. The craters that pock their surfaces are records of ancient collisions, each one a frozen moment from the early solar system when debris was still flying in every direction. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its mountains are built fast and violently. Io has no impact craters to speak of because its surface is constantly being buried under fresh lava. The mountains there rise and fall on timescales that would seem rapid even by Earth standards. Some of Io's peaks reach heights comparable to Earth's tallest mountains, built not by plate collision, but by the intense squeezing and stretching that Jupiter's gravity puts on the Moon as it orbits. Pluto, small and cold and far from the Sun, has mountains of water ice that rise roughly 11,000 feet. Water ice at Pluto's temperatures is as hard as rock. It behaves like rock. It fractures and shifts and builds peaks just as stone does here on Earth. The same physical rules, applied in a completely different environment, produce something that looks surprisingly familiar. This is one of the quieter wonders of the solar system. Wherever you find a world with enough mass to hold itself together, you tend to find mountains. The forces that make them, heat rising from a core, pressure building in a crust, impacts from space, are not rare. They are common. They are what happens when matter gathers and energy moves through it. Earth is not special because it has mountains. Earth is special because its mountains are alive in a way no other worlds are. They are being built and worn and rebuilt in an endless cycle, fed by the heat of the planet's interior and shaped by the water and wind at its surface. They breathe slowly over millions of years, rising and falling like the chest of something vast and patient, resting in the dark between the stars. A mountain does not stand alone. It never has. Every peak you see belongs to something larger, something that stretches for hundreds or even thousands of miles across the face of the Earth. Mountain ranges are the true unit of the mountain world. A single summit is just the most visible part of a much longer story. The Himalayas, for example, do not end at Everest. They run for roughly 1,500 miles across 5 countries: India, Nepal, Bhutan, China, and Pakistan. Nearly 50 peaks in that range rise above 26,000 feet. They form a wall so high and so long that they split the weather systems of an entire continent. To the south, warm, wet air from the Indian Ocean piles up against them. To the north, the Tibetan Plateau sits cold and dry, cut off from that moisture. One range, 2 completely different worlds on either side. This is one of the most important things a mountain range does. It divides. It creates boundaries that air and water cannot easily cross. Scientists call this the rain shadow effect. The wet side of a range catches the moisture. Clouds rise, cool, and drop their rain or snow on the windward slopes. By the time that air spills over the top and down the other side, it has lost most of its water. The land on the far side grows dry. Sometimes it grows into desert. The Atacama Desert in South America sits in the rain shadow of the Andes. It is one of the driest places on Earth, and the Andes made it that way. But a mountain range does not only divide, it also gathers. High peaks pull moisture from the sky. They force air upward, cooling it, bringing rain and snow from clouds that might otherwise drift past without dropping a single drop. The mountains of the Pacific Northwest in North America catch enormous amounts of rain and snow this way. Those slopes stay green and dense and wet. Forests grow thick there, fed by the water the mountains pull from the Pacific air. The range acts like a comb, dragging moisture out of the wind. The ranges of the world are not scattered randomly. They tend to cluster along the edges of tectonic plates, those great slabs of rock that make up Earth's outer shell. The ring of fire, a belt of volcanic and seismic activity that circles the Pacific Ocean, is also home to some of the longest mountain chains on Earth. The Andes run along the western edge of South America for about 4,300 miles, making them the longest mountain range above sea level on the planet. They formed because the Nazca Plate, a section of ocean floor, has been sliding beneath the South American continent for tens of millions of years. The pressure of that collision pushed the land upward. It is still pushing. The Andes are still rising. Ranges also shape the rivers that flow from them. A mountain range acts like a spine. Rain and snowmelt flow away from it in all directions, feeding streams that grow into rivers. The Andes feed the Amazon. The Himalayas feed the Ganges, the Brahmaputra, and the Yangtze. The Rocky Mountains in North America feed the Colorado and the Missouri. Hundreds of millions of people depend on rivers that begin as snowpack on a distant peak. The range and the river are one system, connected by gravity and water and time. Even the soil of the lowlands owes something to the mountains above. Rivers carry tiny ground-up pieces of rock down from the heights. Over thousands of years, those particles settle in valleys and plains, building some of the most fertile land on Earth. The great river deltas of Asia, places where hundreds of millions of people grow food, are made partly from the slow grinding of Himalayan stone. The mountain crumbles, and the crumble feeds the world. Animals move along mountain ranges too. The ranges act as corridors, long connected strips of habitat that allow creatures to travel between regions. They also act as barriers, separating populations of animals long enough that those populations slowly become different from each other. New species form along the edges of ranges, shaped by the particular conditions of altitude and slope and weather. A mountain range is not just stone. It is a force that shapes life, divides it, connects it, and slowly changes it over time. Everything around a mountain range is touched by it. The air, the water, the soil, the animals, the people. The range reaches out in all directions, quietly organizing the world at its feet, one slow season at a time. Mountains hold time inside them, not in a vague or distant way. Literally, physically, in the layers of rock you can see with your own eyes if you stand at the right cliff face and look. Each band of color, each stripe of stone, is a chapter written in mineral and pressure over millions of years. Reading those layers is one of the great skills of geology, the science of Earth's rocks and history. The oldest exposed rock on Earth's surface is found in a place called the Acasta Gneiss in northern Canada. Gneiss is a type of rock that forms deep underground under enormous heat and pressure. The Acasta Gneiss is roughly 4 billion years old. That is almost as old as the planet itself. When you look at that pale, banded rock, you are looking at something that existed before the oceans took their current shape, before complex life began, before almost everything we know about the living world. Mountains can expose rock like that. Erosion, the slow wearing away of stone by wind and water and ice, strips away younger layers over time. What sits beneath gets revealed. A mountain range that has been eroding for hundreds of millions of years can bring ancient rock to the surface, rock that would otherwise be buried kilometers underground. The Appalachian Mountains of eastern North America are among the most eroded ranges on Earth. They were once as tall as the Himalayas. Now they are gentle, rounded ridges, worn down over roughly 480 million years of slow erosion. What remains is some of the oldest exposed rock in North America. Some mountains contain rock that began as ocean floor. When tectonic plates, the massive slabs of Earth's crust, collide, the seafloor can get pushed upward rather than pulled down. Marine fossils, the preserved remains of ancient sea creatures, have been found near the summit of Mount Everest. Tiny shells and the outlines of sea organisms are locked into limestone near the top of the highest mountain on Earth. That limestone formed at the bottom of a warm, shallow sea called the Tethys, which existed before the Indian subcontinent began its long, slow collision with Asia. The sea floor rose. The mountain grew. The shells came with it. The rate at which mountains grow is almost impossible to imagine on a human timescale. The Himalayas rise at roughly 5 millimeters per year in some places. That is about the thickness of a few stacked coins. Over 1 million years, that adds up to 5 kilometers of new height, though erosion constantly works against it. The mountain grows and wears at the same time, and the balance between those two forces determines how tall it gets and how long it stays that way. Some mountains are growing faster than others. The southern Alps of New Zealand rise at a rate that scientists consider unusually fast, partly because the erosion there is also unusually fast, driven by heavy rainfall. The two forces, uplift and erosion, are nearly matched. The mountains stay at roughly the same height even as enormous amounts of rock are constantly being added from below and stripped away from above. It is a kind of slow, grinding balance that has held for millions of years. The deepest canyon on Earth is not the Grand Canyon. It is the Yarlung Tsangpo Grand Canyon in Tibet, carved by a river that drops through the eastern edge of the Himalayan range. At its deepest, it reaches roughly 5,300 meters below the surrounding peaks. is more than 3 times the depth of the Grand Canyon. The river that carved it, the Yarlung-Tsangpo, eventually becomes the Brahmaputra River, one of the great rivers of South Asia. The canyon exists because the river has been cutting downward at almost the same rate the land has been rising around it. The mountain rises, the river cuts, the canyon deepens. Rock in mountains can reach extreme temperatures. In volcanic mountain regions, lava at the surface can exceed 1,200 degrees Celsius. At the same time, the summit of a high peak nearby might sit at minus 40 degrees Celsius on a winter night. Both extremes exist within the same mountain system, sometimes within a few kilometers of each other. The same geological forces that push rock upward into freezing air also drive heat toward the surface from below. Mountains are record keepers. They hold the oldest rock, the deepest canyons, the highest fossils, the fastest rising ridges. Every extreme on land seems to find its way to a mountain. They are where the planet shows its full range, from the ancient and still to the violent and fast, all written in layers of stone that have been building since long before anything walked the earth. High on the mountain, above the last thin line of trees, the world turns white. Snow falls quietly. It falls on bare rock and open ridges. It falls into deep bowls carved into the mountainside, places called cirques, where the wind cannot reach and the cold holds everything still. In these sheltered hollows, snow does not melt. It only builds. Year after year, new snow falls on top of old snow. The weight of each new layer presses down on the layers below. Slowly, over many years, the snow at the bottom stops being snow at all. The air is squeezed out. The crystals are crushed together. What was once light and soft becomes dense blue-white ice. This is how a glacier is born. Not in a single storm, but in the slow, patient accumulation of centuries. Glaciers are not still. They look still, but they move. The ice flows under its own weight, pulled gently downhill by gravity. Most mountain glaciers move only a few centimeters each day. Some move faster. The Jakobshavn Glacier in Greenland, one of the fastest glaciers on Earth, moves roughly 40 to 50 meters per day. But the glaciers that carve mountain valleys move far more slowly than that. They grind, they press, they drag boulders and grit along the rock beneath them like sandpaper pulled across wood. This grinding is called glacial abrasion. The rock flour it produces is so fine it floats in meltwater streams. It turns those streams a pale, milky blue-green. If you have ever seen a glacial lake and wondered why the water looks almost turquoise, that color comes from this powder. Millions of particles of crushed rock suspended in the water, catching the light. The glacier makes the color. The mountain makes the glacier. Everything connects back to the slow work of ice on stone. The shapes that glaciers leave behind are some of the most beautiful forms on Earth. A valley carved by a river is V-shaped, narrow at the bottom. A valley carved by a glacier is U-shaped, wide and flat at the floor, with steep walls rising on both sides. These U-shaped valleys are one of the clearest signs that a glacier passed through long ago. The Yosemite Valley in California is a perfect example. Its flat floor and sheer granite walls were shaped by glaciers that retreated roughly 10,000 years ago. The ice is gone, but the shape it left is still there, enormous and precise. Glaciers also leave behind something called moraines. These are long ridges of rock and debris that the glacier pushed ahead of itself or dropped along its sides as it moved. A moraine looks like a low wall of jumbled stone. It marks the farthest point the glacier reached before it began to retreat. Scientists read moraines the way others read old maps. They show exactly where the ice once was, how far it reached, and when it began to pull back. Snow itself has its own quiet details worth noticing. A single snowflake forms around a tiny particle of dust or pollen high in the atmosphere. Water vapor freezes onto that particle in a six-sided crystal shape. The exact shape depends on the temperature and humidity of the air the crystal falls through. No two snowflakes follow the exact same path through the atmosphere, which is why no two are exactly alike. Each one is a record of the air it traveled through. Scientists study snowflake shapes to understand atmospheric conditions at different heights. On the highest peaks, snow that falls in winter does not always melt in summer. above a certain elevation called the snowline, temperatures stay cold enough year-round that snow persists. The snowline sits at different heights depending on latitude. Near the equator, it sits very high, around 5,000 meters or more. Near the poles, it drops almost to sea level. Mountains near the equator, like Kilimanjaro in Tanzania, carry permanent ice on their summits, even though they sit in a tropical region. The cold of altitude overrides the warmth of latitude. The ice on Kilimanjaro is shrinking. Scientists have measured a dramatic loss of its glacial ice over the past century. The ice fields that once covered the summit broadly have pulled back significantly. This is happening on mountain glaciers around the world. The ice that took centuries to build is retreating within decades. The glaciers that carved these valleys, that colored these rivers, that shaped these wide, open floors of stone, are slowly growing smaller. But even in their retreat, they reveal something. As the ice pulls back, it uncovers rock that has not seen sunlight in thousands of years. Fresh stone, pale and unmarked. The mountain underneath, patient and unchanged, waiting quietly all along. The mountains do not keep their weather secret. They make it. They shape it. They force it into being with nothing more than their height and their mass. But for most of human history, people who lived near mountains simply accepted the weather that came down from the peaks without fully understanding why it behaved the way it did. Early mountain travelers noticed something strange. The higher they climbed, the colder it became. This seemed to make no sense. They were climbing closer to the sun. The sun should have made things warmer. For centuries, this puzzle sat unanswered. Philosophers and scholars offered guesses. Some believed the cold came from the stone itself. Others thought the peaks were simply too far from the warm earth below. The true answer took a long time to arrive. It came slowly, through careful observation. In the early 1600s, the Italian scientist Galileo helped refine the thermometer, a device for measuring temperature with precision. Before that, temperature was mostly a matter of feeling and guessing. With better instruments, scientists could finally attach numbers to what they experienced. Explorers began carrying thermometers up into the mountains. and recording what they found. The numbers told a clear story. Temperature dropped as altitude rose. Every 1,000 meters of elevation brings a drop of roughly 6.5 degrees Celsius. This is called the environmental lapse rate. It is one of the most important patterns in mountain weather. The reason is not distance from the sun. The reason is air pressure. High up on a mountain, the air is thinner. There are fewer air molecules packed together. Thin air holds heat poorly. It cannot trap warmth the way dense, low-altitude air can. The sun's energy passes through thin air without warming it much. So the peaks stay cold even as the valleys below bake in summer heat. This understanding changed how scientists thought about the atmosphere. That thin shell of air wrapped around the earth like a soft and invisible skin. Mountains also force weather to happen. When a mass of warm, moist air moves across flat land and hits a mountain range, it has nowhere to go but up. As it rises, it cools. Cool air cannot hold as much moisture as warm air, so the moisture condenses, forming clouds. Those clouds grow heavy and release their water as rain or snow. This process is called orographic lift, from the Greek word for mountain. It is the reason one side of a mountain range can be lush and green, while the other side sits dry and pale. The man who helped make this process clear was a Scottish meteorologist named Alexander Buchan. In the 1860s, he studied how air masses behaved as they moved across different elevations. His careful records helped build the foundation of modern weather science. He showed that mountains were not passive features of the land. They were active participants in the movement of air and moisture across entire continents. On the dry side of a mountain range, something else happens. As air descends, it compresses and warms. This dry, warm wind that flows down the far side of a mountain is called a Foehn wind in the Alps and a Chinook wind in the Rocky Mountains. Indigenous peoples of the North American plains had names for the Chinook long before European scientists arrived. They called it the snow eater. It could raise temperatures by 20 degrees Celsius in a matter of hours, melting snowpack almost overnight. Their knowledge was precise and practical. Science eventually caught up with what they had long observed. Storms build differently near mountains too. Thunderstorms form more often over mountain ranges than over flat land. The rising air currents that mountains generate push moisture high into the atmosphere, where it cools rapidly and forms the towering storm clouds called cumulonimbus. These clouds can reach 15 kilometers into the sky. Lightning strikes mountain peaks with particular frequency. The high, exposed ridges offer the shortest path between the charged cloud and the ground below. Benjamin Franklin's invention of the lightning rod in the 1750s was partly inspired by observations of lightning striking tall structures. Mountains themselves had long served as natural lightning rods, their peaks scarred and split by centuries of strikes. The dark, jagged silhouettes of high ridges carry that history in their shape. All of this, the lapse rate, the orographic lift, the Furhan winds, the towering storms, was figured out piece by piece. Each observer added a small truth to a larger picture. The mountains were patient teachers. They kept producing the same weather, the same patterns, the same cold and wind and sudden cloud, until the people watching finally understood what they were seeing. The peaks did not change. The understanding did. Mountains do more than shape the weather above them. They also shape the water beneath them, and that water travels much farther than most people expect. Every major river system on Earth traces its origins back to high ground. The Ganges begins in the glaciers of the Himalayas. The Amazon draws much of its water from the Andes. The Nile reaches back to the highlands of Ethiopia and Central Africa. The Colorado River begins as snowmelt on the Rocky Mountains. Thousands of kilometers from the desert canyons, it eventually carves. Mountains are the source. Everything downstream is a consequence. The reason is simple, but easy to overlook. Mountains catch precipitation that flat land never receives. They force moisture-laden air upward, cool it, and pull rain and snow from it. That water collects on the slopes. It seeps into the ground, fills cracks in the rock, and slowly moves downhill. Some of it feeds springs. Some of it joins streams. All of it is moving always toward lower ground. A mountain does not hold cold water, it releases it steadily over months and years. Snow is the most surprising part of this process. A snowpack is not just frozen water sitting still. It is a slow-release system. Snow that falls in winter stays locked on the slopes through the cold months. Then, as temperatures rise in spring and summer, it melts gradually. This gradual release keeps rivers flowing through the dry season, long after the last rain has fallen. Without mountain snowpacks, many of the world's great rivers would shrink to a trickle in summer. Scientists call mountains the water towers of the world, and the name fits. They store water at altitude and release it slowly to the valleys below. The Himalayas alone feed 10 of Asia's largest rivers: the Indus, the Brahmaputra, the Mekong, the Yangtze, the Yellow River. All of them begin in Himalayan ice and snow. These rivers support the lives of more than 1 billion people. The food, the drinking water, the irrigation for crops. It all starts on those high, cold slopes. The mountains are so far from the people they support that the connection is easy to miss. But it is real, and it is constant. Here is the part that surprises even people who study rivers. Mountain glaciers act as a second layer of storage, deeper and slower than snowpack. A glacier holds water for decades, sometimes centuries. It moves slowly downhill, melting at its lower edge, releasing water into streams year after year. During a drought, when snowpack is low and rainfall is scarce, glaciers keep rivers alive. They are a kind of long-term reserve, built up over centuries of snowfall, drawn down slowly in times of need. The rivers that mountains feed also carry something else. They carry rock. Water moving downhill picks up sediment, the tiny particles of sand and silt and mineral that break off from mountain slopes. Rivers transport this material enormous distances. The sediment that the Ganges carries eventually settles in the Bay of Bengal, forming one of the largest river deltas on Earth. The Mississippi carries sediment from the Rockies and the Appalachians all the way to the Gulf of Mexico. Mountains erode slowly, but rivers carry that erosion to the sea grain by grain over millions of years. The mountain does not stay on the mountain. It travels. That sediment is not just rock. It is mineral-rich material that fertilizes the land it settles on. The great river deltas of the world, the Nile Delta, the Mekong Delta, the Ganges Delta, are among the most fertile places on Earth. They are fertile because mountains upstream are slowly dissolving and sending their minerals downriver. The richness of the soil in a river valley is, in part, a gift from the peaks far above. There is one more surprise worth sitting with. Rivers do not just carry water away from mountains. They also shape the mountains themselves. As rivers cut downward through rock, they remove material from the base of mountain ranges. This removal actually allows the mountains to rise slightly higher. The rock below, relieved of weight, pushes upward in a process called isostatic rebound. The mountain and the river are not separate things working against each other. They are part of the same slow process, each one influencing the other across vast stretches of time. The water that falls as snow on a high peak may take years to reach the sea. Along the way, it carves canyons, feeds forests, fills aquifers, and nourishes cities. It carries pieces of the mountain with it, and in doing so, it connects the highest places on Earth to the lowest in one long, quiet, unbroken flow. That slow, unbroken flow does not stop at the riverbank. It continues upward into the soil itself, into the thin, dark layer of earth that clings to the mountain slopes. And that soil, fragile, patient, alive, is one of the most important things a mountain makes. Soil on a mountain does not appear quickly. It takes an enormous amount of time. A single inch of healthy mountain soil can take hundreds of years to form. It begins with bare rock. Wind, rain, frost, and ice slowly break that rock apart into smaller and smaller pieces. This process is called weathering. The mountain, which once seemed so permanent and hard, is always being worn down, grain by grain, into something softer. Those tiny rock grains are just the beginning. Soil needs more than crushed stone. It needs life. The first living things to arrive on bare mountain rock are often lichens. Those flat, crusty patches of gray and orange and pale green that you see clinging to boulders. Lichens are not quite plants. They are a partnership between a fungus and a tiny organism that can capture sunlight together, they release weak acids that slowly eat into the rock surface. They are among the first pioneers on bare stone, and they begin the long work of turning rock into something a plant can one day use. When lichens die, they leave behind a thin layer of organic matter, the remains of living things. Mosses move in next, finding just enough material to take hold. Their roots push into tiny cracks, widening them. Water follows. Frost expands those cracks further. More rock breaks apart. More organic matter builds up. Over centuries, the soil deepens just slightly. Then small flowering plants arrive. Then grasses. Each generation of life adds something to the soil when it dies, and the soil grows richer and deeper in return. This slow building of soil is happening on mountain slopes all over the world, right now, quietly and without pause. It is one of the great background processes of the living earth. Mountain soils are different from the soils of flat lowlands. They tend to be thinner because gravity and rain are always pulling material downhill. They also tend to be younger because erosion constantly strips the older layers away. But what they lack in depth, they often make up for in mineral richness. The rock beneath a mountain slope is often full of elements that plants need. Calcium, potassium, magnesium, iron. As that rock weathers, those minerals become available. Rain carries them downward into the soil, where plant roots can reach them. The steepness of a mountain slope also shapes what kind of soil forms there. On very steep ground, soil barely has time to build before it slides or washes away. On gentler slopes and in mountain valleys, soil can accumulate over long periods. These valley soils are often the deepest and most productive on a mountain. Farmers have known this for thousands of years. Mountain valleys around the world, in the Alps, the Andes, the Himalayas, have been farmed for millennia. Because the soil there is rich and the water is close, there is something else that shapes mountain soil, and it comes from above. The trees and plants that grow on mountain slopes are constantly dropping leaves, needles, bark, and branches. This organic material, called leaf litter, slowly breaks down on the forest floor. Fungi and bacteria and tiny insects work through it, turning it into humus, the dark, spongy, nutrient-rich part of soil that gives it its deep brown color and its ability to hold water. A mountain forest is always feeding its own soil. The trees grow from the soil, and when they die, they return to it. That water-holding ability matters enormously. Mountain soils act like sponges. When rain falls or snow melts, healthy mountain soil absorbs the water slowly and releases it gradually. This is what keeps mountain streams flowing even during dry seasons. The soil holds the water back, then lets it go steadily over weeks and months. When mountain soils are damaged or stripped away, that sponge effect disappears. Water runs off fast, floods come quickly, and streams run dry between rains. So the soil connects the mountain to everything below it. It connects the rock to the plant to the animal, the mountain to the river, and the river to the sea. The thin, dark layer of earth on a mountain slope is not just dirt. It is the bridge between the stone world and the living world, built slowly over centuries, grain by grain, life by life, in a process so quiet and so steady that it is easy to forget it is happening at all. There is a line on every tall mountain where the trees stop. It is not a sharp line exactly. It is more like a slow fading. The forest thins. The trees grow shorter and more twisted. Their branches reach sideways instead of up, bent by wind that never really stops. And then, after a stretch of these small, struggling trees, the forest simply ends. Above that point, there are no more trees at all. This boundary is called the Timberline, or sometimes the tree line. It is one of the most striking edges in the natural world. The Timberline sits at different heights on different mountains, near the equator, where the sun is strong and the air stays warm. Trees can grow as high as 12 or 13,000 feet. In the mountains near the poles, where cold air settles in even during summer, the tree line may sit as low as a few hundred feet above sea level. The height of the Timberline is not set by the mountain itself. It is set by temperature. Trees cannot survive where the growing season is too short or too cold for them to complete their yearly cycle of growth. Above the Timberline, the world changes completely. The soil becomes thin and rocky. The wind grows sharp and constant. Snow can fall in any month of the year, and yet life does not disappear. It simply changes form. Low-growing plants hug the ground to stay out of the wind. Mosses spread across the rocks in soft green and gray patches. Tiny wildflowers bloom in bursts of color during the brief, warm weeks of summer. This zone above the trees is called the Alpine Zone, and it holds a quiet, stubborn kind of beauty. What is remarkable is that the timberline is not fixed. It moves over long stretches of time. As climates shift, the tree line creeps upward or retreats downward. Scientists have found ancient tree stumps high above today's tree line in many mountain ranges around the world. Those stumps are the remains of forests that grew during warmer periods thousands of years ago. The climate cooled, the trees died back, and the tree line dropped. The mountain remembered the change in its own quiet way. Right now, the timberline is moving again. As global temperatures rise, trees are slowly advancing upward into zones that were once too cold for them. Researchers studying mountains in Europe, North America, and Asia have all recorded this shift. In some places, the tree line has moved upward by hundreds of feet over the last century. The change is slow, measured in decades, but it is real and it is steady. This upward creep of the forest has consequences that reach far beyond the mountain itself. The alpine plants that live above the tree line are adapted to cold, open conditions. As trees move in, those plants lose their space. Some of them have nowhere higher to go. Scientists are watching several alpine plant species carefully, concerned that they may shrink in number as the forest rises around them. The animals that depend on those open alpine zones face the same pressure. The timberline also affects how mountains handle water. Forests hold snow differently than open alpine meadows do. Trees catch snow on their branches and shade the ground, slowing the melt. When the tree line rises, the pattern of snowmelt changes with it. Water that once trickled down slowly through open meadows may begin to flow differently, affecting the streams and rivers that millions of people depend on far below. There is something deeply patient about the timberline. It has been shifting back and forth for as long as mountains mountains have existed. During ice ages, it dropped far down the slopes. During warm periods, it climbed high. The trees have always been testing the cold, always pushing a little further up when conditions allowed, always retreating when the cold returned. It is a slow conversation between the living world and the climate, carried on over thousands of years without pause. And the mountain holds the record of every chapter of that conversation. The buried stumps, the pollen preserved in ancient lake sediments, the rings inside old trees that grew near the edge of survival. All of it tells the story of how the Timberline has moved through time. Scientists can read those records and piece together a picture of past climates stretching back many thousands of years. The line where the trees end is not just a boundary. It is a living record of change. It shows us where the mountain stands today, and it hints at where the mountain is going. Everything on the slope above and below that line is connected, shifting together, slowly and without hurry, the way mountains have always changed. Above the timberline, the trees give way to open sky. The slope becomes bare rock and low scrub and wide fields of snow. The air grows thin. The wind picks up. And yet, life is here. Animals have found ways to live in this cold, bright, difficult world. They are remarkable creatures, shaped by thousands of generations of survival at the edge of what is possible. The light up here is different from anywhere else on Earth. At high altitude, the atmosphere above you is much thinner. There is less air to scatter and filter the sun's rays. So the light that reaches you is sharper, more intense, almost white. Ultraviolet radiation, the invisible part of sunlight that causes sunburn, is far stronger here than at sea level. Scientists estimate that ultraviolet levels increase by about 10 to 12% for every 1,000 meters of elevation gained. The animals that live here have adapted to that brightness in ways that are quiet and extraordinary. The snow leopard moves through this world like a pale ghost. Its thick, smoky gray coat is marked with dark rosettes, and those markings help it blend into the rocky, snow-patched slopes of Central Asia's high mountains. Snow leopards live at elevations between 3,000 and 5,000 meters, fur-covered paws act like natural snowshoes, spreading their weight across the snow. Their long, heavy tails, nearly as long as their entire bodies, help them balance on steep terrain and wrap around their faces like a scarf when they sleep in the cold. Their pale eyes are adapted to the bright, high-altitude light. They are built for this world in every detail. The yak is another creature shaped entirely by altitude. Wild yaks live on the Tibetan Plateau and in the surrounding mountain ranges, often above 4,000 meters. Their lungs are larger than those of lowland cattle. Their blood carries more red blood cells, which means more oxygen moves through their bodies with every breath. Their thick outer coat of coarse hair hangs low, nearly touching the ground, and beneath it is a dense layer of soft, fine undercoat that traps heat close to the skin. When sunlight falls on a yak's dark coat, the black absorbs warmth. On a cold, bright mountain morning, that absorbed heat can make a real difference. High in the Andes, the vicuña grazes on the sparse, golden grasses of the Puna, the high plateau that sits above 4,000 meters. The vicuña is a relative of the camel, and like the yak, it has blood that is unusually rich in red blood cells. Its wool is among the finest natural fibers on Earth, so fine that a single strand is thinner than a human hair. The Inca people once considered vicuña wool sacred. Only royalty wore garments made from it. The animal itself was protected by law. Today, the vicuña is still protected, and its population has recovered from near extinction to several 100,000 animals across the Andes. Birds find their own ways to thrive in the thin, bright air. The bar-headed goose migrates over the Himalayas twice each year, flying at altitudes that can exceed 7,000 meters. Researchers have tracked these birds crossing directly over some of the highest peaks on Earth. Their blood is specially adapted to pull oxygen from the thin air with unusual efficiency. They fly mostly at night and in the early morning when temperatures are lower and the air, though still thin, is denser and slightly easier to breathe. The sight of these birds crossing a pale dawn sky above the highest mountains on Earth is one of the quieter wonders of the natural world. Even insects live here, jumping spiders have been found on the slopes of Mount Everest above 6,000 meters, making them among the highest dwelling animals ever recorded. They survive on tiny insects blown up from lower elevations by mountain winds. The wind carries more than just cold air. It carries food, seeds, and small creatures, connecting the high mountain world to the valleys far below. The light at altitude does one more thing worth noticing. At sunrise and sunset, the thin atmosphere scatters the longer wavelengths of light, the reds and oranges, across the sky in colors that are deeper and more vivid than anything seen at lower elevations. Mountain climbers often describe the alpenglow, that warm rose-pink light that settles on the peaks just after sunset, as one of the most beautiful sights they have ever seen. The animals that live here see that light every day. They move through a world painted in sharp whites and deep blues, and at the edges of the day, warm gold. They have made their home in one of the most visually stunning places on Earth, and they carry that brightness in the very structure of their bodies. People have always followed the animals upward. Long before there were roads or maps or written records, small groups of humans climbed into the high places and stayed. They built their lives there in the thin, cold air, surrounded by rock and wind and that deep, vivid light. And over thousands of years, their bodies and their cultures changed to fit the mountains around them. The Tibetan people are perhaps the most studied example of this. They have lived on the Tibetan Plateau, a vast high region averaging over 4,000 meters above sea level for at least 10,000 years. At that altitude, the air holds roughly 60% of the oxygen available at sea level. For most people, that would mean constant exhaustion, headaches, and a body struggling to function. But Tibetan people carry a gene variant, a small change in their DNA that helps their blood carry oxygen more efficiently. Scientists believe this adaptation developed over thousands of generations. The mountain shaped the people who lived on it, slowly and quietly, the way it shapes everything else. The Quechua people of the Andes carry a similar story. Their ancestors built the Inca civilization high in the mountains of South America, with cities like Machu Picchu sitting at roughly 2,400 meters above sea level. Quechua people tend to have larger lung capacity than people raised at lower elevations. Their hearts pump more blood with each beat. These are not small differences. They are deep physical changes written into the body over generations of mountain life. The mountain asked something of the people, and the people answered. Sound moves differently in the high places. At altitude, the air is thinner, and sound waves travel through it with less energy. Voices carry in strange ways. A shout can echo off a cliff face and return seconds later, changed and hollow. The wind itself becomes a constant sound, a low, steady roar that fills the background of every moment. Mountain communities around the world developed ways of communicating across these vast, echoing distances. In the Atlas Mountains of Morocco and across parts of the Alps, people used yodeling, a technique of rapidly switching between chest voice and a higher, lighter tone to carry messages across valleys that were too wide to cross easily. The sound of yodeling is designed for the mountain. It cuts through wind. It bounces off stone. It travels farther than a normal speaking voice ever could. In the Himalayas, the sound of bells has carried across mountain passes for centuries. Buddhist monasteries built at high altitude use large brass bells and long horns called dungchen, instruments that produce deep, resonant tones that travel far through cold mountain air. Monks have played these instruments at dawn and dusk for over 1,000 years. The sound rolls down the valleys and across the snowfields, steady and low, like the mountain itself is breathing. The Sherpa people of Nepal have guided climbers on Himalayan peaks for generations. Their knowledge of the mountain is not just physical. It is cultural, passed from parent to child, built from centuries of watching how the weather moves, how the snow settles, how the wind shifts before a storm. They know the sounds of the mountain in ways that no instrument can fully measure. The crack of ice that signals an unstable slope, the particular hiss of wind that means a weather change is coming, the soft, settling sound of fresh snow that tells an experienced ear whether the ground beneath is safe. This knowledge has saved countless lives. Mountains also produce sounds that no human ear was present to hear. When glaciers calve, that is, when large chunks of ice break away from a glacier's edge and fall, the sound is like a cannon shot. It echoes for miles. The crack travels through the ice itself, a deep vibration that scientists can record with sensitive instruments. These recordings reveal that glaciers are not silent. They groan and shift and pop as the ice moves under its own enormous weight. A glacier is always in motion, always speaking in low frequencies that sit just at the edge of what humans can detect. The people of the high places learned to listen. They had to. The mountain communicates through sound and silence, through the behavior of animals, through the color of the sky at evening. Living at altitude means paying close attention to everything around you, because everything carries information. The wind brings weather. The animals signal danger. The ice tells you where not to walk. Mountain cultures around the world share this quality of deep attention, a way of moving through the world with all the senses open, reading the signs that the mountain offers to those patient enough to hear them. That quality of deep attention shaped something else entirely. It shaped the way people thought about mountains themselves, not just as places to survive, but as places that meant something, as places that held a kind of power no human could fully name. Across every culture that ever lived near a great peak, the mountain became sacred. It became the place where the earth reached toward the sky, and where something larger than human life seemed to dwell. The numbers behind this idea are older than writing. Ancient peoples studied the stars from high places. They noticed that mountains offered a clearer view of the heavens, above the haze and smoke of the valleys below. From those high vantage points, they began to track the movements of the sun and moon with remarkable precision. They found patterns. They found rhythms. And those rhythms, repeated year after year with perfect reliability, felt like proof that the universe followed rules. Rules that were elegant. Rules that were beautiful. Rules that a mountain, standing still and patient, helped them see. The Himalayas hold a special place in this story. Mount Kailash, a peak in western Tibet that rises to 6,638 meters, has never been climbed. Not because it is impossible, but because it is considered too sacred to set foot upon. 4 major religions, Hinduism, Buddhism, Jainism, and the ancient Bon tradition of Tibet, all regard Kailash as the most holy mountain on earth. Each tradition describes it differently, but all of them agree on one thing. This mountain is the center, the axis around which the world turns. In Sanskrit, the ancient language of India, the word for this concept is axis mundi, meaning the point where heaven and earth meet. What is remarkable is that this idea appears independently in cultures with no contact with each other. The ancient Greeks believed Mount Olympus, their highest peak at 2,917 meters, was the home of the gods. The Norse traditions described a great world tree rooted at the center of the cosmos, connecting the S above and below. The Aztec pyramids were built to imitate mountains, to create sacred high places where none existed naturally. Across thousands of miles and thousands of years, human minds arrived at the same conclusion. Height equals closeness to something greater. The mathematics of mountains supported this feeling in ways those ancient peoples could not have fully understood. A mountain's height above sea level changes the atmosphere around it in measurable ways. At the summit of Everest, the air pressure is roughly 1/3 of what it is at sea level. There is 1/3 as much oxygen available with every breath. The human body at that altitude begins to behave differently. The mind can feel altered. Visions become possible. Ancient peoples who climbed to high places and experienced these effects may have interpreted them as contact with the divine. In a sense, the mountain's own physics created the experience of the sacred. There is also the matter of proportion. Mountains follow mathematical ratios that appear throughout nature. The slope of a stable mountain, the angle at which loose rock and soil can pile before it slides, is called the angle of repose. For most dry rock and gravel, this angle sits between 30 and 45 degrees. This same range of angles appears in sand dunes, in the shape of volcanic cinder cones, in the piles of grain in ancient storehouses. The universe seems to prefer certain angles, certain proportions. The mountain, built forces that know nothing of beauty, arrives at shapes that feel balanced and right to the human eye. The ancient builders knew this instinctively. The great pyramids of Giza were built at an angle of roughly 51 degrees, steeper than the angle of repose, which required careful engineering to hold their shape. The builders were imitating mountains, but refining them, making them more perfect. The math of the mountain became the math of the sacred structure. The two ideas folded into each other across centuries. Mountains also mark time in ways that feel almost ceremonial. The shadow of a peak moves across the valley below like the hand of a great clock. Ancient communities used these shadows to mark the seasons, to know when to plant and when to harvest. The mountain's geometry, the precise angle of its slopes, the height of its summit, determined the length and direction of that shadow. A mountain in this way was a calendar, a tool, a gift from the earth to the people living in its care. Every culture that looked up at a great peak saw something true. They saw that the mountain was not random. It followed rules. It moved in patterns. It offered information to those willing to pay attention. The sacred and the mathematical, it turns out, were never separate things. Mountains did not only inspire awe, they also stood in the way. For most of human history, a mountain range was a wall. It blocked armies. It separated languages. It kept one people from knowing another people existed. But every wall, if you look long enough, has a door. And in the mountains, those doors were the passes. A mountain pass is a low point in a ridge, a place where the rock dips down just enough for a path to thread through. These gaps formed over millions of years, carved by glaciers or cut by ancient rivers. They were accidents of geology, but to the humans who found them, they were everything. The most famous network of trade routes in history ran through some of the most forbidding mountain terrain on Earth. The Silk Road was not a single road. It was a web of paths that connected China to Central Asia, Persia, and eventually the Mediterranean world. Much of it wound through the Pamir Mountains and the Hindu Kush, ranges that rise above 5,000 meters in places, where the air is thin and the winters are brutal. Merchants carried silk, spices, glass, and gold. they also carried ideas, religions, and languages. The mountains did not stop this exchange. The passes made it possible. The Khyber Pass is one of the most traveled mountain corridors in history. It cuts through the Hindu Kush range along what is now the border between Pakistan and Afghanistan. The pass sits at about 1,000 meters above sea level, which is modest by mountain standards, but the cliffs on either side rise steeply, and the path through is narrow. Armies used it for thousands of years. Alexander the Great moved his forces through the Khyber region in the 4th century BCE. So did the Mughal Emperor Babur centuries later. The same geology that made the pass accessible also made it defensible. Whoever controlled the high ground controlled the route. In the Alps, the Great St. Bernard Pass connects Switzerland to Italy through a gap that sits at nearly 2,500 meters. Roman legions used it. Merchants used it for centuries after that. In 1800, Napoleon moved an army of roughly 40,000 soldiers through it in the early spring, when snow still packed the upper slopes. The crossing took about a week. It was dangerous and exhausting, but it worked because the pass was there, and because someone had learned long before Napoleon exactly where the rock dipped low enough to cross. What is remarkable is how thin the margin was. A pass that sits a few hundred meters higher might have been impassable in winter. A slightly different angle of approach might have exposed travelers to avalanche. The conditions that made these routes usable were precise. The geology had to cooperate. The snowpack had to be manageable. The path had to be wide enough for animals carrying loads. When all of those variables aligned, a civilization could move through the mountains. When they did not, the mountains remained a wall. This is the fragile balance that mountains represent. They are enormous and ancient, but the conditions that make them crossable, livable, survivable are narrow. A shift in climate that adds a few extra meters of snowfall can close a pass for a season or a century. A small earthquake can bring a rock slide down across a path that thousands of people depended on. The mountain does not change its mind. It simply follows the rules of physics and geology. It is the humans who must adapt. The passes also shaped where cities grew. major pass could collect tolls, offer shelter, and trade with everyone moving through. Some of the great medieval cities of Central Asia grew rich this way. Samarkand, in what is now Uzbekistan, sat near the convergence of several mountain trade routes. Its wealth came from being the place where the paths met, where the mountains funneled travelers into a single valley, and where a city could grow up to serve them. Mountains, then, were not just barriers or sacred symbols or sources of water. They were architects of human movement. They decided, in a very real sense, where people could go and how fast they could get there. The shape of a ridge, the depth of a pass, the angle of a slope. These geological facts determined which cultures would meet and which would remain strangers for centuries. The rock did not know any of this. It was simply following the slow logic of pressure and time. But the humans who moved through it, who found the gaps and built the roads and raised the cities, they were reading the mountain's geometry the same way their ancestors read its shadows. Carefully, gratefully, with everything depending on getting it right. And yet, for all that mountains have given us, for all the cities and roads and civilizations that grew in their shadows, there is still so much we do not fully understand about them. The mountains are not finished speaking. Scientists are still listening, still asking questions that have no clean answers yet. That is not a failure. It is an invitation. One of the deepest open questions in geology is how, exactly, the Himalayas got so tall. We know the broad story. The Indian subcontinent drifted north and collided with Asia roughly 50 million years ago. That collision crumpled the crust upward into the highest mountain range on Earth. But the details are still being worked out. Scientists are not entirely sure why the Himalayas rose so much higher than other collision ranges. The forces involved were not unique. Other plates have collided before. Other mountains formed, but none reached quite the same height. Something about the thickness of the crust, or the speed of the collision, or the way the rock behaved under pressure, produced a result that still surprises researchers when they run the numbers. There is also the question of how fast mountains grow and fall. We can measure the rate at which tectonic plates move. We can measure measure erosion. But the relationship between the two is more complicated than it first appears. Some mountains seem to rise faster than erosion can wear them down. Others seem to be losing height faster than the rock beneath them can push upward. The balance point, the moment when a mountain is neither growing nor shrinking, is called isostatic equilibrium. Scientists can define it. They can model it. But predicting exactly when a given mountain will reach it, or whether it already has, remains genuinely difficult. The Earth does not hold still long enough to make the math simple. Beneath the mountains, the picture gets even murkier. The roots of mountain ranges, the deep sections of crust that extend downward like the keel of a ship, are still being mapped. We know they exist because of how gravity behaves differently over mountain ranges than over flat plains. The rock below a mountain is less dense than the rock below a plain, and that difference is measurable. But the exact shape of those roots, how deep they go, how they change over millions of years, is still an active area of research. Some scientists believe that when a mountain range erodes away at the surface, its root slowly floats upward too, like a melting iceberg rising as it loses mass. Evidence suggests this happens, but the full picture is still coming into focus. Mountains also shape climate in ways that researchers are still untangling. The basic mechanism is well understood. A mountain range forces moist air upward. The air cools, and rain falls on the windward side. The other side stays dry. This is called a rain shadow. The Atacama Desert in South America, one of the driest places on Earth, exists largely because the Andes block Pacific moisture from reaching it. But how mountain ranges interact with large-scale wind patterns, ocean currents, and long-term climate cycles is far more complex. Scientists are still building models that can accurately predict how a new mountain range, or the slow erosion of an old one, changes rainfall patterns across an entire continent over millions of years. And then there is the question of mountains and life. We know that mountain ranges create isolated pockets of habitat. A valley on one side of a ridge may have completely different plants and animals than a valley on the other side. Even if the two valleys are only a few miles apart, This isolation drives the evolution of new species. The mountains act as walls, keeping populations separate long enough for them to change. The Andes alone contain more bird species than any other mountain range on Earth, partly because of this effect. But scientists are still working out the precise relationship between mountain geography and the rate at which new species appear. How high does a ridge need to be to truly separate two populations? How long does the separation need to last? The answers are not yet fully known. What we do know is that the mountains are not passive. They are not simply rocks sitting still while the world moves around them. They push air upward and pull rain from clouds. They split rivers and divide species. They raised cities and buried others. They are still rising in some places and falling in others, right now, tonight, while you rest. The questions that remain about them are not gaps in our knowledge to be embarrassed by. They are open doors. They are the reason scientists still climb, still drill, still measure, still wonder. The mountain keeps its secrets slowly, but it does give them up in the end to those who are patient enough to ask. The mountains are patient. They have stood for millions of years, and they will stand for millions more. But nothing lasts forever, not even stone. Right now, every mountain on Earth is being worn away. Rain falls on the high ridges and seeps into tiny cracks in the rock. In winter, that water freezes and expands, and the crack grows a little wider. Over thousands of years, this slow splitting breaks boulders into smaller stones, and smaller stones into gravel, and gravel into the fine dust that eventually becomes soil in a valley far below. The mountains are generous that way. They give themselves away, grain by grain, to the world beneath them. The Appalachian Mountains in the eastern United States were once as tall as the Himalayas. Scientists believe this ancient range rose up more than 480 million years ago, pushed skyward by the same kind of colliding plates that built every great range on Earth. But the Appalachians had no new collision to keep them growing. Erosion worked on them steadily, century after century, and today their highest peak, Mount Mitchell, stands at just under 6,700 feet. That is still a tall mountain, but it is a whisper of what once was. The Himalayas are still rising. India continues to push northward into Asia at roughly the same speed that your fingernails grow, about 2 inches per year. The rock buckles upward, but erosion works just as steadily in the other direction. The two forces are in a slow, quiet contest, and for now, the uplift is winning. Everest gains a small amount of height each year, but this will not go on forever. In time, the movement will slow. The plates will settle, and the great peaks will begin their long descent. In about 250 million years, scientists believe the continents will come together again. They have done this before. The supercontinent called Pangaea, which held all of Earth's land in one vast body, broke apart roughly 175 million years ago. Before Pangaea, there were other supercontinents. Earth has a long habit of gathering its land together and then pulling it apart again. When the next great collision comes, new mountain ranges will rise where ocean floors once lay. The Himalayas may be long gone by then, worn down to gentle hills, while entirely new peaks push up from the crust somewhere we cannot yet predict. The sun plays a role in all of this too. Over billions of years, the sun grows slowly brighter. Scientists estimate that in about 1 billion years, the sun will be roughly 10% more luminous than it is today. That extra energy will warm the oceans and increase the rate of weathering. The chemical process by which rock slowly dissolves and breaks down. Warmer, wetter conditions could strip mountains away faster than they form. The balance between building and wearing down may shift in ways that reshape the entire surface of the planet. And in about 5 billion years, the sun will reach the end of its life as a stable star. It will expand into what astronomers call a red giant, swelling outward far beyond its current size. The inner planets may be consumed entirely. Earth's fate is uncertain, but the surface as we know it, the oceans, the atmosphere, the mountains, will be gone long before that final moment. The rock itself will remain, transformed, melted, remade into something entirely new. But here is the quiet wonder in all of this. The atoms that make up every mountain on Earth have already been through fire. They were forged ancient stars that exploded long before our sun was born. The iron in granite, the calcium in limestone, the silicon in quartz, all of it came from those distant, long-dead stars when our mountains eventually erode and scatter and melt and reform. Those same atoms will still be here. They will become something else, perhaps new rock on a future continent, perhaps part of a new world forming around a younger star. Nothing is truly lost. Matter changes shape. It moves through systems. A mountain that falls becomes the sediment of a sea, and the sediment of a sea becomes the stone of a future range, and the future range rises into clouds that have not yet formed above a sky we will never see. The mountains you know tonight, the ones that stand dark and still against the stars, are not permanent, but they are part of something that is. The slow turning of matter through time, through heat and pressure and water and wind, goes on and on. The earth keeps making itself new. It always has. It always will. Mountains do more than rise. They reach into the sky and change the very air around them. They split storms in half. They decide where rain falls and where it does not. They shape the climate of entire continents, and they have been doing this for hundreds of millions of years. When wet air blows in from the ocean, it rises when it meets a mountain range. As it climbs, it cools. Cool air cannot hold as much water as warm air. So the moisture falls. It falls as rain on the windward side, the side facing the wind, and the forests there grow thick and green and full of sound. But on the other side of the mountain, the air has already lost its water. It descends dry and warm. The land there turns to scrub, to dust, to desert. This effect has a name. Scientists call it a rain shadow, and it explains some of the driest places on Earth. The Atacama Desert in South America is one of the driest places on the planet. Some parts of it go years without a single drop of rain. The Andes Mountains stand to the west, pulling moisture from Pacific winds before it can reach the desert floor. The Atacama sits in the shadow of those peaks, parched and still, while the mountain slopes above it catch what little cloud drifts by. The same pattern appears in the American West. The Sierra, Nevada range in California catches rain from the Pacific, feeding forests and rivers on its western slopes. The Great Basin to the east sits dry and wide, shaped by that same long shadow. The Himalayas do something even more dramatic. They stop the monsoon. Every summer, warm, wet air rises from the Indian Ocean and moves north across the subcontinent. When it meets the wall of the Himalayas, it cannot pass. It rises, cools, and releases enormous amounts of rain across South Asia. This monsoon feeds rivers, fills reservoirs, and waters crops that billions of people depend on. Without the Himalayas standing there to catch that moisture, the pattern of rainfall across the entire region would be completely different. The mountains are not just scenery. They are infrastructure. On the other side of the Himalayas, the Tibetan Plateau, that vast, cold, high expanse of land, sits in the rain shadow. It is one of the largest and highest plateaus on Earth, averaging more than 4 kilometers above sea level. The air there is thin and dry. The plateau actually heats up intensely in summer, and that heat draws the monsoon winds northward, helping to drive the whole system. The mountains and the plateau work together, pulling and shaping the air, guiding the rains across a continent. Mountains also cool the world. Snow and ice on high peaks reflect sunlight back into space. This reflection, scientists call it albedo, keeps energy from being absorbed by the land. Glaciers store enormous amounts of fresh water and release it slowly through summer melt, feeding rivers long after the last winter snowfall. The Hindu Kush, the Alps, the Rockies, the Andes, all of them act as frozen reservoirs, releasing water steadily through the warm months, keeping rivers flowing when rain alone would not be enough. And the mountains affect temperature far beyond their slopes. The Tibetan Plateau influences wind patterns across Asia. The Rockies shape the path of the jet stream, that fast river of air high in the atmosphere, which in turn steers storms across North America. A mountain range thousands of kilometers away can influence whether a city gets a cold winter or a mild one. The air does not know borders. It flows where the land tells it to flow. Step back far enough and the picture becomes clear. Mountains are not obstacles, They are regulators. They distribute water. They guide wind. They store cold. They create the conditions for forests and rivers and farmland and life. Every range on Earth is part of a larger system, breathing with the atmosphere, exchanging heat and moisture with the oceans, shaping the world that everything else depends on. The mountains you can picture right now, those dark peaks standing quiet against the night sky, are not separate from the rain falling somewhere far away, or the river running through a valley you have never seen, or the desert stretching silent under stars on the other side of a ridge. They are all the same story. The mountain rises, the cloud forms, the rain falls, the river runs, the valley blooms. It has always worked this way. It works this way tonight. And somewhere in the world, right now, a mountain is catching a cloud, and the rain is beginning to fall. And somewhere deep beneath the surface of the earth, the story is already beginning again. Right now, tectonic plates, those vast, slow-moving slabs of rock that make up the outer shell of our planet, are pressing against each other. The pressure builds over millions of years. The rock bends, it folds, and slowly, so slowly that no human eye could ever watch it happen, new mountains are being born. The planet is not finished. It has never been finished. It is still building. Scientists believe that the collision between the Indian subcontinent and the rest of Asia, the same collision that raised the Himalayas, is still happening today. The Himalayas are still growing. Each year, Mount Everest rises by a small fraction of a millimeter. It is a tiny movement, but over 10 million years, tiny movements become the highest peaks on Earth. The mountains we see today were once flat ground. The flat ground of today may one day carry snow. There are places on Earth where new volcanic mountains are forming right now beneath the ocean. The Hawaiian Islands were built this way, one eruption at a time, over millions of years. And southeast of the big island of Hawaii, a new seamount, an underwater mountain called Loihai, is growing on the ocean floor. It rises about 3,000 meters from the seafloor already. Scientists estimate it will break the surface of the ocean in roughly 100,000 years. A new island is coming. A new mountain is on its way. The ocean does not know this yet, rock does. The earth keeps its own kind of time. A human life is a breath. A civilization is a long exhale. But a mountain range is a slow, deep sleep that lasts hundreds of millions of years. The Appalachians in eastern North America were once as tall as the Himalayas are today. Wind and rain and ice wore them down, grain by grain, over 300 million years. What stands there now are the ancient roots of something enormous. The mountains you see are always somewhere in their story, rising or resting, or slowly returning to the sea. And the material never disappears. The rock that erodes from a mountain washes into rivers. Rivers carry it to the ocean. The ocean floor slowly sinks beneath a continent. The rock melts. It rises again as magma, that hot, liquid rock deep inside the earth. One day, it erupts, and the mountain begins again. Nothing is lost. Everything is borrowed and returned. This is the quiet truth that mountains carry. They are not permanent. Nothing on earth is permanent. But impermanence is not the same as fragile. The planet is strong and patient and endlessly creative. It has been making mountains for 4 billion years. It will keep making them long after every human name for them has been forgotten. Tonight, the mountains stand where they have always stood. The snow on the high peaks glows faintly under the moon. The glaciers are still. The valleys below are dark and quiet. A river moves through the silence, carrying a little bit of mountain with it, grain by grain, toward the sea. The wind is calm. The stars are out, and the planet turns slowly and steadily, the way it has turned for billions of years. From far enough away, Earth looks like a smooth blue marble, but up close, it is rough and ancient and alive. The mountains are its texture. They are the wrinkles in a planet that has been thinking for a very long time. And every wrinkle has a story, a collision, an eruption, a slow fold of stone under unimaginable pressure. Every peak is a record. Every valley is a memory. You are part of this story too. The calcium in your bones was made in stars. The water in your body has cycled through clouds and rivers and glaciers for billions of years. The air you are breathing right now has moved over mountains, through forests, across oceans, and back again. You are not separate from the planet. You are made of it. You are resting on it right now. And it is holding you the way it has always held everything that lives here. The mountains that are yet to come will rise slowly, long after tonight. But tonight, the ones that are here are enough. They are standing in the dark, quiet and enormous, doing what they have always done, holding the sky up a little, catching the clouds, letting the rain fall. Rest now. The planet is still turning. The mountains are still standing. Everything is exactly where it should be. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.